Now let's solve one or two problems for the method of changing independent variable, that is x to let's say z. Okay, let's look at the problem. Cos x d2y by dx square plus sin x dy by dx minus 2y cos cube x is equal to 2 cos 5x. Right? Looks complicated, right? Okay. Uh, this is d2y. This is dy by dx. So this is p. This is going to be q. But after converting this equation into standard form, because cos x is there here. So divide the entire equation by cos x. What do we get? Cos x gets cancelled. We are left with d2y by dx square plus sin x by cos x gives you tan x dy by minus 2y 2 cos cube x by cos x. Cube becomes a square. 2 cos square x y is equal to 2 cos 5x by cos x gives you cos 4x. Right? So this is in the standard form. And here P is equal to tan x. Q is equal to minus 2 cos square x. R is equal to 2 cos 4x. Right? Now remember, in the previous session we looked at two methods of picking up z, how to decide what z should be. So dz by dx square should be equal to the magnitude of q. Yes, that's what we decided. Now here in this case, this is nothing but magnitude, so we ignore the minus sign. 2 cos square x. This becomes dz by dx is equal to, on this side it becomes 2 cos square x, which is equal to square root of 2 cos x. In the previous session, I had just briefly given this as an example. And now to get z, we have to integrate this, right? So this becomes root 2, which is a constant, remains as it is. Integral of cos x is sin x. So our chosen independent variable z would be equal to, so coming back to our equation, 2y by dz square plus p1 dy by dz plus q1y is equal to r1. Yes. Now here p1 would be what? P1 would be, and this you have to remember, d2z by dx square plus p dz by dx. If you have done the derivation, if you have understood the derivation, then it will be easier for you to remember this. Okay, and the whole thing divided by dz by dx square. This would be what? Here, if you look at it, d2z by dx square is what? Do we know that? No, we don't have that, right? So let's find d2z by dx square would be equal to, we use this, so root 2 as it is, right? And we have to differentiate cos x. So differentiating cos x gives us minus sin x, right? So which means it is minus root 2 sin x. So here we end up with minus root 2 sin x plus p is what? Remember, p is tan x. So plus tan x times dz by dx. Dz by dx is what? Where is it? Dz by dx is root 2 cos x. So root 2 cos x divided by dz by dx square, right? That is 2 cos square x. So 2 cos square x. Okay. Let's simplify this to see what happens. Minus root 2 sin x plus sin x by cos x times root 2 cos x. So cos x gets cancelled. Remember, denominator you have 2 cos square x. And here if you notice, sin x root 2 minus root 2 sin x. So these two get cancelled out. So numerator is 0, so the overall thing is 0. So P1 is, now Q1 would be equal to what? Q by dz by dx square. And here Q is what? Q is minus 2 cos square x. So minus 2 cos square x divided by dz by dx square. That is 2 cos square x. So these two get cancelled out and we are left with 1. That is minus k. R1 is equal to R by dz by dx square, which is equal to, now R is, again if you go back, 2 cos 4x. So 2 cos 4x divided by 2 cos square x. So 2 and 2 cancels out. And here 2 of the cos x's get cancelled. So you're left with cos square x. Now our equation becomes d2y by dz square. Remember, P1 has become what? 0. So it disappears. Then we have Q1y. Q1 is minus 1. So minus y is equal to R1. Now R1 is what? Cos square x. So cos square x. Okay. Now this can be written in D notation. So this can be written as d square minus 1 y is equal to cos square x. Right? Now this cos square x, we should be able to do it in, let's see what is z. Z is sin x, right? So here on the right hand side also, if we get it in terms of z, it would become easier. So since z is equal to something sine, let's convert this into sine. So 1 minus sine square x. Okay. Now 1 minus sine square x, let's see here, z is equal to root 2 sine x, right? Z is equal to root 2 sine x. Now what we want is sine square x, right? So let's square it. We get sine square x, 2 is equal to z square, right? 2, if we bring it to this side, we get z square by 2 is equal to sine square x. So we can write it as 1 minus z square by 2. So this becomes d square minus 1 y. And this we know how to solve it. Yes. Auxiliary equation, m square minus 1 equal to 0. So m square is equal to 1. So m is equal to plus or minus 1. So which means complementary function is c1 e to the power of x plus c2 e to the power of minus x. Now particular interval 1 by d square minus 1 times 1 minus z square by 2. This can be written as minus 1. I am taking minus from denominator, so it becomes 1 minus d square times 1 minus z square by, and this can be written as minus 1 minus d square to the power of minus 1. 1 minus z square by 2. Right? And this can be written in the series form. Right? So minus 1 plus d square plus d4 plus and so on times 1 minus z square by 2. Now let's multiply this. What do we get? Minus, let's keep it outside itself, 1 times, no, 1 times this. So 1 minus z square by 2 plus b square of, let's make this as a square bracket, of 1 minus z square by 2 and so on. Because remember, as we keep differentiating, it will become 0. So minus 1 minus z square by 2. We have to differentiate this now. We have to differentiate it twice. So first time when we differentiate it, what do we get? Minus 2z by 2. Yes, minus 2z by 2. Now this minus 2z by 2 gives us minus z. If we differentiate it once more, what do we get? We get minus 1, right? There's no point in going further in the series because now the next time we differentiate, it becomes 0. Okay, so now minus 1 and 1 gets cancelled out. Minus minus becomes plus and we are left with z square by 2. So what is this? This is your particular integral. So our solution becomes what? Our solution becomes y is equal to c1 e to the power of, I think I have made a mistake here. This would be z. This would be z and this would be minus z, right? See, when you're just doing it in the flow, because you're so used to writing x, 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 be careful, especially when we are doing this method and similar kind of methods where you do substitutions. Okay, so this becomes e to the power of z plus c2 e to the power of minus z and then plus z square by 2. Okay, now remember our solution has to be in terms of x. So c1 e to the power of z is equal to what? Remember, z is equal to root 2 sine x. So this becomes a root 2 sine x plus c2 e to the power of minus root 2 sine x plus z square would be 2 sine square x. So this becomes square. So 2 sine square x by 2. That is 2 get cancelled out. So we are left with c1 e to the power of root 2 sine x plus c2 e to the power of minus root 2 sine x plus sine square x. Right? So that is the method of changing the independent variable. Looks very lengthy, but remember we already know how to solve this equation. Yes? Once we arrive at this, we know how to solve it. So the only thing is how to bring it to this particular form. Okay, that is the critical. Okay, let's do one more problem. Let's say d2y by dx square plus 2 cos x plus tan x dy by dx plus y cos square x is equal to cos 4x. Now here p is equal to 2 cos x plus tan x. Q is equal to cos square x. R is equal to cos 4x. Right? Straightforward, dz by dx square is equal to q, magnitude of q. Anyhow, it is negative is not there, so cos square x. Let's get rid of that square. So we get dz by dx is equal to cos. Now, if we want z, we integrate, we get sin x. We might require d square z by dx square, in which case we differentiate it once more. We get minus sin x, right? Okay. So now in terms of z, our equation becomes p2y by z square plus p1 dy by dz plus q1y is equal to r1. Remember, p1 would be equal to d2z by dx square plus p dz by dx divided by dz by dx square. Let's do the substitutions. d2z by dx square. d2z by dx square is minus sin x. Minus sin x plus p. Now p is what? P is, where is that? P is 2 cos x plus tan x. So 2 cos x plus tan x. dz by dx is what? dz by dx is cos x. So this would be then, so cos x outside the bracket divided by dz by dx, that is going to be dz by dx is going to be it's square, so cos square. Okay, let's solve this. Minus sin x plus 2 cos square x plus sin x by cos x, cos x. So cos x gets cancelled, divided by cos square x. Sin x and sin x gets cancelled, cos square x gets cancelled. We are left with 2. So our P1 is equal to 2. Now we have to figure out Q1. This is going to be Q by dz by dx square, which is equal to Q is cos square x by dz by dx is cos x, but here it is square, so cos square x. So these two cancel out and we get 1. Okay, r1 is equal to r by dz by dx square. Now r is cos square x, no, it's cos 4x divided by cos square x. So this cancels and you are left with cos square x. Now if you look at our z is what? Z is sin x. So if this cos square x can also be written in terms of z, that would be great. So cos square x can be written as minus sin square x, which means it can be written as 1 minus z square. So our equation becomes d2y by dz square, this is z square. Then we have p1, p1 is 2, so plus 2 dy by dz plus q is, q1 is 1, so y is equal to r is 1 minus z square, right? Now we solve this. We know how to solve this. Auxiliary equation, m square plus 2m plus 1 equal to 0. This is nothing but m plus 1 square equal to 0, which means m is equal to minus 1 comma minus 1. That means minus 1 is being repeated. Again, you have to remember that complementary function in case of repeated roots is c1 plus c2 z e to the power of minus. Okay. Now, particular integral would be what? 1 by d square plus 2d minus 1 times 1 minus z square. This can be written as 1 by 1 plus d square, or let me write it in the numerator itself. This can be written as 1 plus d to the power of minus 2 times 1 minus z square. And this can be written in the series form. 1 minus 2d plus 3d square plus minus 4d cube and so on. 1 minus z square. Now let's multiply it. We get 1 minus z square plus 3d square. No, not 3d square, 2d. So 1 times this gives you 1 minus z square minus 2 times differential of 1 minus z square plus 3d second derivative 1 minus z square and so on. Now let's simplify this. Now minus, now 2 times the first derivative. So first derivative would be minus 2z. So minus 2z minus 2 is 4z plus 3 times the second derivative. Second derivative would be minus 2z minus 2. So this becomes minus 3 times 2. So 6. Next derivative, if we go, it will become 0. So we can stop. So this can be written as minus z square minus 4z minus 5. No, here this should be minus into minus plus 4z. So this will be plus. Okay. So this was the particular integral. So solution would be equal to c1 plus c2z e to the power of minus z minus the particular integral, which is, if we take minus out, this becomes z square minus 4z plus 5. And we substitute z back. Z is what? Z is, I think, sine x. Z is sine x. Okay, so c1 plus c2 sine x e to the power of minus sine x minus sine square x minus 4 sine x plus 5. So that is the solution. Now let's look at a snippet of the another problem. Let's say q is equal to 1 by 1 plus x square square. Now in that case, what do we do? Z would be what? Now dz by dx square would be 1 by 1 plus x square square. Yes, which means dz by dx would be 1 by 1 plus x square. And this is where the tricky part comes. You have to remember that if you integrate this, you get z, and the integral of 1 by 1 plus x square is tan inverse of x. If you remember this, great, then the whole thing becomes easy. Or if they have already given to you as part of the question, then no problem. But if it is not given and you have to figure out, then you have to know this particular identity, or rather integral. Okay, anyhow, I think that's enough for today. Bye for now.